Hello, everybody. Welcome back one more time to AP Physics with Mr. O'Hagan. Today, we're going to be talking about Newton's second law for rotation. There it is, already written down for you. Okay, in our last two lessons, last two of these videos that I made, we learned about this thing called rotational inertia, R-O-T-A-T-I-O-N-A-L, inertia, I-N-E-R-T-I-A. And rotational inertia is a capital I, and it's basically the rotational equivalent to mass. This is a measurement of the resistance to a rotating body. It's a measurement of a rotating body's resistance to the change in its velocity, in its angular velocity. Okay. Again, it's an equivalent to mass. It's a rotational equivalent to mass, and mass is a measurement of an object that's translating its resistance to changes in its velocity. Okay. So rotational inertia, rotational mass. We also came up with this idea of torque, T-O-R-Q-U-E, and torque is this Greek letter tau, and torque is a rotational force, if you would, okay? And if you remember, torque was R cross F. Okay, so now, here we go. Let's take these two ideas and let's do Newton's second law with them, okay? Newton's second law, the net torque net, will cause an object that's rotating, has some type of rotational inertia, to have an angular acceleration. And this is very similar in form to Newton's second law, the way we're used to seeing it. A force net will cause a mass to have an acceleration. Okay, very similar. And of course, Newton's second law is a vector quantity, so the direction of the net torque and the direction of the angular acceleration are the same. All right, so here's Newton's second law. Pretty easy. It's directly relatable to Newton's first law, but I want to do a sample problem with you to kind of show Newton's second law in action. And here's what we're going to do. I'm going to take an object, and let's say the object is fairly small, and let's say it has a mass equal to, what do I want it to be? 10 kilograms. All right, and this object is at the end of a string, and this string is held here. So this is going to be my pivot, P-I-V-O-T, pivot point, P-O-I-N-T. And we're going to let this mass go. And it's just going to, it's going to, as soon as you let it go, it's going to, can I get this right? Probably not. It's going to follow this type of path, basically a circular path, and then continue up this way. And what I'm looking to know is, let me give you this. Let's say the length of this string, R equals 0.5. Okay, that'd be meters, of course. All right, so 0.5 meters. Okay, so now let's say this is what I want to find out. I want to know what is the acceleration, all right, the angular acceleration of this object. Okay, so it's going to be doing this. What is alpha? All right. Let's start with Newton's second law for rotation. All right. Torque equals I alpha. So move this out of the way. Sorry about that. So angular acceleration, alpha, equals the torque divided by the rotational inertia. So I got to figure out these two objects, these two quantities, torque and rotational inertia. I'll do those down here, and then we'll fill them back in up here and see what happens. All right. And let's switch colors for this. No, I'll just continue on with what I got going here. All right. So the torque. Torque, remember, equals R cross F. Since the radius, there's a force. I forgot the force. The force is going to be the force of gravity. That's what's going to pull it down. And the force of gravity is mg, and the mass is 10, and g is negative 10, or 10 down. I'm going to use 10 instead of 9.8. All right, so this ends up being a 10 times 10 in the down direction. So the force of gravity ends up being 100 newtons. So that's easy. Okay, so back to what we were doing here. Our torque equals R cross F. All right, easy peasy lemon squeezy. The radius is 0.5, 0.5. The force is 100. And because these are at right angles, because the radius and the force are at right angles, this is going to be the most torque you can get. All right, that's the torque. Remember, it's RF sine of the angle between them. Well, the angle between them is 90 degrees. Sine of 90 is 1. So here we go. All right. Basically, this is R perpendicular force, or this is R force perpendicular. Because they're perpendicular to each other, we're just done. Okay, but anyway, this is 50 Newton meters. Okay, so that's the torque. Rotational inertia. All right, how do we figure that out? This is going to be a point mass. Remember at the beginning I said it's really small size-wise compared to the radius it's at. So that's kind of the definition of a point mass. How small is small? Who knows? But anyway, I'm saying this is a point mass. Okay, so rotational inertia for point mass is mr squared. Well, let's plug in our numbers here. It's 10, and what's my radius? My radius is 0.5, 0.5, and that's going to be squared. So 10 times a half is 5 times another half is 2.5. So this ends up being 2.5 kilogram meters squared. Okay, so those are my two numbers that I'm going to plug into Newton's second law for rotation. All right, so we've got, what do we got here? 50 Newton meters divided by 2.5 kilogram meters squared. So what is that going to be? It's going to be 50 divided by 2.5. I think that's 50 divided by 25 is 2. 50 divided by 2.5 has got to be 20. All right, so that's going to be 20. Now, what are the units here? All right, I got to think this through. The units for newtons are kilogram meters per second squared. So that's the units for newtons. So what we've got is we've got 20 kilogram meters over second squared times meters, and that whole thing divided by kilogram meters squared. All right, so what do we got here? We got meter squared gets rid of those. Kilograms go away. So this ends up being 1 divided by second squared. All right. Except 1 over second squared. Oh, yeah. That's the units for an angular acceleration. But let's agree to lie and call them radians per second squared. So it's radians per second squared. Okay. So that's my angular acceleration. Nicely done. Easy peasy lemon squeezy. All right. But now, there's kind of an interesting tie-in here. If I have this on a string and I let it go, the instant you let it go, the only force that's on it is this force of gravity. It's not until it swings down a little bit that you get an inward force because of the rope, causing it to change direction. But for that very first instant, it's straight down. So we can figure out, and I'll just make a little room here. Hopefully I have enough room for this. We can figure out its acceleration when it first drops. Actually, you don't even have to figure out the acceleration. We know the acceleration. The acceleration due to gravity is 10 meters per second squared, and it's down. All right, the very first instant. I mean, if you're not sure about how that works, all right, Newton's second law, force net equals mass times acceleration. Acceleration's force net over mass. What did we say the net force was? 100. What's the mass? The mass was, where'd the mass go? The mass is 10. And what do we back up to? We're at 10 meters over second squared. All right, so my angular acceleration is 20 radians per second. My linear acceleration is 10 meters per second squared. Down, okay, that's all right. I'm just worried about the size. But here's what's kind of cool. There's a way to go between angular acceleration and linear acceleration. So let's do that. Let's turn this linear acceleration into an angular acceleration and see what happens. All right, so how do we do that? We start with SOAR. All right, arc length equals angle times radius. And then I'll switch over the velocities because it would be velocity equals angular velocity times radius. So acceleration, and this is, of course, is the tangential acceleration, which this is, tangential acceleration, equals angular acceleration times radius. So therefore, the angular acceleration is the linear acceleration divided by the radius. What's my linear acceleration? That's 10 meters per second squared. Divided by the radius, what's my radius? 0.5 meters. 10 divided by a half. Hey, angular acceleration is 20, 1 over second squared. Okay, let's lie. 20 radians per second. Okay? So this is Newton's second law for rotation. And I just did a simple case with a point mass. And I showed you how you could figure it out, coming up with both the torque and the angular and the rotational inertia. But then I showed you how it actually does work with the things we already know. You figure out the regular linear acceleration of it, and then, hey, guess what? They do relate to each other through this thing we learned a long time ago, SOAR, and then second derivative of that. Okay? All right, so anyway, that is Newton's second law for rotation. One more time right there, Newton's second law for rotation. I hope you learned something. Adios.